this sort of world. This is what's out there on the other side of the agent, the thing it's interacting with. And what's going to happen is there's this loop over time. You can think of this loop where the agent is interacting with the environment, and at every step it's seeing something of the world. It gets some observation where it's seeing a snapshot of the world at this moment. The agent's wandering around seeing stuff. And the environment is generating what that observation will be and what the reward is. So if you imagine, this is the Atari environment or something, then there's some actual real Atari game that's generating the next observation, the next screen, and the score. But we're not controlling that part. We have no control over the environment except through this channel here. We get to influence the environment solely by the actions that we take within that environment. So the agent influences the environment by taking actions within it. A robot can move around and influence it where it is within the environment or where objects are, and so forth. Okay? So an interaction between agent and environment. And this just goes on, and the trial and error loop that we define for reinforcement learning is basically a time series of observations, rewards, and actions, and that time series defines the experience of the agent. And that experience is the data that we use for reinforcement learning. So the machine learning problem of RL is concerned with this source of data, this stream of data coming through, observations, actions, rewards.
Do we always limit ourselves to just strictly a scalar reward? Because, for example, I can imagine interacting with a world and I make a decision that, increases my standing with my boss but pisses off my girlfriend, for example, and I might,
Good. Okay, so the question was, do we have to limit ourselves to a scalar reward? So I thought people were suspiciously silent, so let's go back to this hypothesis. So the reward hypothesis was that the reward is a single scalar feedback signal, and a scalar feedback signal is sufficient to describe everything we mean by goals. So the question is, well, sometimes there are maybe different conflicting goals that you might have, and how do you know which of those it is that you care about optimizing at any given time? And so I guess the RL view of that would be to say that ultimately the agent has to pick actions. And to pick actions, you have to be able to weigh up these different goals, because ultimately you have to pick an action. You have to decide whether you're going to meet your girlfriend or whether you're going to, do the other thing you care about. Go to work. Stay late at work or hang out with your girlfriend. And you have to pick amongst those ultimately. And so to pick amongst them, you need to be able to compare them. And in order to be able to compare two things, you have to be able to line them up on an axis, which kind of implies that you have some scalar, there's some scale on which you can compare them, which can be converted into a scalar reward. So there's always a conversion. Ultimately, there must be a conversion into a single thing that you can decide over, and so a scalar reward ultimately must be enough. That's the RL view. Not everyone has to agree with that. Okay. So this stream of experience that comes in, this sequence of observations, actions, rewards, we call it the history. So the history is what the agent has seen so far. So each step it takes its action, sees an observation, sees a reward, all the way up to the current time step t. And the history, ht, is basically the sequence of everything it's seen so far. And that's, in some sense, this is all the observable variables. Like, there might be other things hiding inside the environment, but the agent doesn't know about those. It can't observe those things. And so in some sense, they're irrelevant to the algorithms that we create. The algorithms that we create can only be concerned with what the agent can actually see. Remember, we're trying to build that brain. The algorithm sits in that brain. And so we should only concern ourselves with what the brain is actually exposed to. And so you can think of this as like the sensory motor stream of a robot or an embodied agent. But this also applies more generally. A game-playing agent or a trading agent, it has its own sensory motor stream of what the inputs are that it's seeing and the decisions that it's able to take. There's some well-defined interface between agent and environment, and we just get to control and see this stream of stuff that's coming into the agent from its environment. And what happens next actually depends on this history. So the agent, our algorithm, we get to build something which is essentially a mapping from this history to an action. So that's our goal, is to build a mapping. An algorithm is a mapping from one of these histories to picking the next action. So what happens next from the agent's point of view depends on the history. And what the environment does is the environment looks at what it's received. It looks at the history of what's happened in terms of the agent, and it also looks at the history, and it uses this history to decide what it's going to do next in terms of what observation it's going to emit at the next time step. So this history literally determines the nature of how things proceed. The history determines what happens next. But it's not very useful. The history isn't very useful because it's typically enormous. You know, we want to have agents that have long lives and can deal with microsecond interactions, and each of these observations may be a video, and we don't want to have to go back to this history every time. And typically what we talk about instead is state. And so state is like a summary of the information that's used to determine what happens next. So in other words, if we can replace the history by some concise summary that captures all the information we need to determine what happens next, then we've got a much better chance to do some real things with our machine learning. And we're going to spend some time talking about state. I think it's a really crucial concept that's widely misunderstood, and I really want to carry this over really carefully. So formally, what is state? So every time step t, we can construct this state, which is a function of the history. So it's just any function of the history. That's the definition of state. So, you know, a valid definition of state would be to only look at the last observation, for example, and just ignore everything that's come before, or to look at the last 4 observations. That's actually what we did in Atari. Pretty simple. Okay. But there's many different definitions of state, and what I want to pick apart now is at least 3 different definitions of state to understand what they really mean and how they relate to each other. So the first definition is what we call the environment state. So the environment state is basically the information that's used within the environment to determine what happens next. So if you think about it, there's some in this world, imagine this is, you know, the robot interacting with some real environment. That real environment has some sort of set of numbers determining what's going to happen next. Or if this is the Atari emulator, the emulator has some internal state that's going to decide what that emulator does next. Or if this is, you know, a factory, that what happens to that factory has some process that's going to decide what happens next. And there's some set of numbers that determines what happens next from the environment's point of view, based on what it's seen so far, its history, and there's some state that summarizes everything it's seen, and which will spit out the very next observation and reward. And so we call that the environment state. This is literally, you know, what, if you kind of informally were to say what state is the environment in, it's the set of numbers that is contained in here, the information that is necessary to determine what happens next from the environment's perspective. So the special thing about the environment is that it's not usually visible to the agent. So, you know, we don't get to look inside our crystal ball, and we don't get to see everything that's happening within the environment. If you've got some robot walking around in the world, it doesn't know the state of all of the atomic configuration of Ayers Rock in Australia. It only gets to see what's in front of it in this video stream that's coming through to it right now. So the environment state, this set of numbers that's determining what happens next, isn't usually visible to the agent. So it's more like a formalism that helps us understand what an environment is than something practical that helps us build our algorithms here. Our algorithms cannot depend on these numbers. Our algorithms don't see these numbers. Our algorithms just see the observation coming in and the reward and the actions coming out. And furthermore, even if we could see this information, sometimes it might not be the right information that we would like to use to make effective decisions here. So again, you know, the configuration of Ayers Rock isn't probably very relevant to the robot that's wandering around this room right now. It needs to be able to look at its own stream and understand what's locally around it to be able to make good decisions. And so actually having its own subjective representation may be a good thing. Yes, question?
If you put a lot of agents together influencing the same environment, do you get any sort of self-organized behavior patterns or anything like that?
Okay, so the question is about multi-agent systems. So I just want to say one thing about multi-agent systems, which is essentially they're beyond the scope of this course, but let me just briefly say that from the perspective of each individual agent, it can consider all of the other agents that it's interacting with to be part of the environment. So from the perspective of one brain here, the fact that there are other brains wandering around in this environment doesn't really change the formalism. It doesn't have to change the formalism. There's just one agent interacting with them. Your question, I think, is whether the emergent behavior shows some patterns between the brains here and the brains there. It can, and there's a lot of work on that, but it's kind of beyond the scope of what I'm going to talk about in this course. Right. So the environment state doesn't tell us anything useful for actually building algorithms. We don't see that. So instead, we talk about the agent state. The agent state now is the set of numbers that actually lives inside our algorithm. So within our algorithm, we're going to have some set of numbers that we use to basically capture exactly what's happened to the agent so far, summarize what's gone on, summarize everything it's seen so far, and use those numbers to basically pick the next action. So whatever information we choose to store and capture here is what we call the agent state. Whatever information is used to pick our next action, that's what we call the agent state. And that's our decision. Our decision is how to process those observations and what to remember and what to throw away. And that, there are many different choices there which we'll talk about. So, and this is the information that's used by our reinforcement learning algorithm. So when we build an RL algorithm, we'll really always be talking about the agent state, that we'll be thinking about, formalisms where we take an agent state and we build something that picks actions from our state. And that's really our goal then, is to really understand how to pick actions given some state that's summarized everything we've seen so far. And this state could be any function of history. This is our choice. We can build this function. That's part of the agent. The agent gets to decide what this function is going to be, how it's going to convert the history of all of the actions and observations and rewards it's seen so far into a useful, say, vector of information that's going to be used to characterize its future behavior. Okay, so that was two definitions of state, agent state and environment state. Now here's a more mathematical definition of state, which we call the information state, or sometimes called the Markov state. And the Markov state, or the information state, basically is an information theoretic concept. It tells us when we've built a state representation that contains all useful information from the history. So what we're going to do is we're going to define something. We're going to define a Markov property. So this is the Markov property. It's probably familiar to those of you who've studied anything to do with Markov chains or anything like that. It's the same idea. And the Markov property basically says that the probability of the next state, conditioned on the state you're in, is the same as the probability of the next state if you showed all of the previous states to this system. In other words, you can throw away all of the previous states and just retain your current state, and you would get the same characterization of the future. So let's just try and understand what that really means. So I like to think of it this way, that what this is really saying is that the future, what's going to happen in the future, if you have the Markov property, then the future is independent of the past given the present. In other words, that you only need to store this ST here. If you've got this state representation S and it's Markov, you can throw away the whole rest of the history. You don't need it, because that history doesn't give you any more information about what will happen in the future than the state that you have. That's what the Markov property means. It means you can throw away everything that came before, just keep your state, and you're good, because you haven't given up anything. That state still characterizes everything about the future, all future observations, actions, rewards. The distribution over those events is the same, conditioned on your state, as it is conditioned on the whole history. So you can just give up this, work with something much more compact, and everything will be fine. So that's the definition of a Markov state. So we can throw away the history now. And another way to say the same thing is that the state is a sufficient statistic of the future. So this state here fully characterizes the distribution over future actions, observations, and rewards. So once we have this state, we can say everything that there is to say about that distribution. Yeah, question?
I think you said at the beginning, though, that the reward comes at many time steps after the action, the observation, and the action.
Yes.
So, I mean, how does that reconcile with the fact that you're throwing everything away except the previous time step?
That's fine. So all we're saying here is that the way that this environment is going to evolve going into the future, that everything we can say about the future, the distribution of events that might happen to us, conditioned on this state is the same as if we conditioned on the full history. So we still have to figure out how to take the right actions. We still have to figure out what the optimal behavior will be. All this tells us is that if we make decisions based on S, those decisions can still be optimal because we haven't thrown away any information. We haven't talked yet about how to make decisions based on S rather than H.
Yeah. In your example of a helicopter, for instance, because clearly where it goes next depends on where it was before.
Okay, so the question was, how does this fit in with the helicopter example? So for the helicopter example, a Markov state for the helicopter would be the current position, velocity, angular velocity, angular position of the helicopter would be roughly a Markov state for the helicopter. Once you know all of those things, and maybe you need to know the wind direction and things like that as well, but if you know all of those things, it doesn't matter what the position of the helicopter was 10 minutes ago. that doesn't make any difference to where the helicopter will be at the next moment. All that matters is where it is now, and the wind direction, and that will fully determine what will happen to the helicopter at the next moment. You don't need to remember this detailed history of its previous trajectory, because it's irrelevant. In contrast, let's say you took an imperfect state representation that's non-Markov, like you just had the position but not the velocity. Okay? Now, where the helicopter is does not fully determine where it will come next, because you don't know how fast it's moving, and so you have to look back in time to figure out actually what its velocity is and what its momentum will be, all these kind of things. Okay, so that's the information state or the Markov state.
Can I just ask one question? On this, we're saying that the state, if we know the state, then we know everything there is to know about future states.
Yes.
But that itself is not necessarily very helpful, because the state might be nothing to do with the reward.
Okay, so this history, don't forget that the history includes all rewards. So to say that it's a sufficient statistic of the future means that it's a sufficient statistic of all future rewards. So that, by definition, means that a Markov state contains enough information to characterize all future rewards. Okay, so I want to give two just brief examples before we move on. So one thing to note is that the environment state, if only we had access to the environment state, that would be great, because the environment state is Markov. By definition, the environment state fully characterizes what will happen next in the environment, because that's what the environment is using to pick its next, the next observation it's going to emit is and the reward. So sort of by definition, the environment state is Markov. Also by definition, if we keep the entire history of everything, that is also a Markov state. It's just not a very useful one. But if we retain everything and make our decisions based on the entire history contains as much information as the entire history. It's sort of tautological, so therefore it's Markov. So these are two examples where we can, to show that there's always a Markov state. It's always possible to come up with some Markov state. The only question is, in practice, how do we find a useful representation? Okay, so let's just make this concrete with one example. So this example, we've got this rat, and I want you guys to be the rat. Okay, and I'm going to be the evil experimenter who's going to either give you a piece of cheese, or if you don't do what I like, then I'm going to electrocute you. Okay, so here's a few sequences that you observe. So you're learning by trial and error. So light comes on, you pull a lever, hear a bell, and then zap, I electrocute you. Okay, sorry. Second episode, you hear a bell, see a light come on, you pull a lever again, and you get a delicious piece of cheese. Okay? Third episode, pull a lever, see a light come on, pull a lever again, hear a bell, and now you need to predict for me. Are you going to get electrocuted, or are you going to get a delicious piece of cheese? Okay? So let's have a show of hands for, based on this experience that you've seen so far, if you were this rat, how many people think that you'll be electrocuted? Okay, a lot of people. How many people think that you'll get a delicious piece of cheese? Okay, a few. And can someone say why you thought, so someone from the electrocution, why did you think you'd be electrocuted?
Because of the bell. So from the past experience, when you hear a bell after the lever, you get electrocuted.
Okay.
While in both cases you have seen a light before the lever, so we're not sure about it.
Right, so the comment was that the recent history was the same. So we've seen light, lever, bell here, light, lever, bell here. So from the last three, we would expect there to be electrocution. So another way to say that is that if you're a rat and your agent state, the state that you're using to make your decisions is the last three things in the sequence, then you would believe that you're going to be electrocuted. However, that's not the only choice for state. You might, for example, choose the agent state to be counts for the lights, the bells, and the levers. So if that was your agent state, then you might count them up and say, hey, look, in this example, we see the lever's being pressed twice, the light has come on once, and the bell's sounded once. So that's exactly the same as this second episode here. So if that's our representation of state, we would expect that the cheese would appear now. So it should be clear that what we believe will happen next depends on our representation of state. So what about this one? What if the agent state is the complete sequence? What will happen next? If we think that the next thing which happens is the complete sequence we've seen so far, what will happen next? We don't know. And that's another legitimate case. It might be that actually the environment, what happens next does depend on the entire sequence, and you just have to see all 4 things before you know what happens next, in which case we just don't have the data to decide yet. So the state representation really defines what happens next in some way that can be characterized in all kinds of different ways. And in some sense, our job is to build an agent state that's useful, that is effective in doing the best job of predicting what happens next. Okay. So let's finally, on this part, just talk about a couple of special cases. So fully observable environment, this is what we're going to work with for a lot of the remainder of the course. So this is the nice case. So this is the type of environment where we get to see everything. The agent literally gets to see what's going on in the environment state. So it gets to look inside, see the numbers inside the environment, and work with those numbers. So that's the best case. And so another way to say that is that all of these things collapse to the same quantity. So the observation that we see is the same as the agent state, which is the same as the environment state. We get to see the environment state and use it as our agent state. And when we work with this type of representation, we come up with the main formalism for reinforcement learning, which is called a Markov decision process, or MDP for short. And we'll spend the next lecture actually understanding MDPs in more detail, because they're a really powerful tool. But I really want people, when we go through the rest of the course, to remember these ideas of state representation, because not everything is fully observable, and it's really crucial that we understand how to deal with these other very realistic problems. And luckily, the MDP formalism, which we'll develop, actually also helps us to deal with those cases too. So what about the other case? The other case is partially observable environments. So this is where the agent indirectly observes the environment. So it doesn't get to see everything about the environment. So for example, a robot with a camera, it might not know exactly where it is unless it has a GPS. Maybe it just gets to see this camera stream. It has to figure out for itself where it is within the room. It has to localize. Or another example would be a trading agent. This trading agent might only observe the current prices, but it might not know, the trends or where these prices are coming from. It has to just figure out what to do next based on partial information. Or a poker playing agent, it only observes the public cards, the cards which are face up on the table, and it doesn't know what's hiding in someone else's hand. These are all examples of partial observability. And in all of these cases, the agent state, we have to build a state that's distinct from the environment state, because we don't know the environment state. We don't know what's in the opponent's hand or what's hiding behind the environment that's driving the prices. We don't know all that information. It may as well not exist as far as the brain is concerned that we're trying to create. So this needs a different formalism, and this is known as a partially observable MDP, or a POMDP. And now our job is to build this agent state. We have to build this SAT. So how do we do that? Well, there's lots of ways we could do it. The naive approach is just remember everything. So remember all of the observations, actions, rewards we've seen so far, and say, hey, that whole thing, that whole sequence is going to be our state. Let's work with it. Or we can build beliefs. This is the probabilistic or Bayesian approach. So at every step you build beliefs over where you think. So you think, okay, I don't know what's happening in the environment, but I'm going to keep a probability distribution over where I think I am in the environment. So I'm going to have some probability that I think the environment state is S1, some probability the environment state is Sn, etc. And this whole vector of probabilities defines the state that we're going to use to actually decide what to do. So you actually keep a whole probability of all of those things. That's not the only choice. Another choice is to do something, you don't need to use probabilities at all. It's not necessary. We can have any numbers we want inside our agent. For example, a recurrent neural network. So that basically means that you take your agent state that you had at the previous time step, and you just take a linear combination of the agent state you had at the last time step with your latest observations, and that gives you a new state. So you just have some linear transformation of your old state to your new state that takes account of the latest observations, have some nonlinearity around the whole thing, and that gives you a new state. So that's the recurrent neural network approach. Okay. Any questions before I think I missed one? Yeah.
Just to clarify, for instance, between these two descriptions in your Atari game, full state would presumably be knowing the rules of the game. So the agent would sort of realize what the rules are.
So the question was, can I clarify what's going on with the Atari example? So let me just jump forward. I have a figure here to help clarify that, which I was going to do later, but maybe it's helpful to do now. So this is what the RL cycle looks like between agent environment in the Atari example. So in the Atari example, we basically have the agent is making its decisions. It gets to take actions, which are to control the joystick. The environment in this case is the actual machine, and it's got some cartridge in it which determines the rules of the game. We don't know what's on this cartridge. We don't get to see it. We don't know how it's picking its next screens that it's going to show us and the next scores. But that cartridge, given the actions that we take on our joystick, will determine both what it shows on the screen and also the score. Those things are fed into the agent, and it gets to take a new action as a result. So the state in this case, the environment state would be the set of numbers. There's 1024 bits in the emulator. It's a 1024-bit machine. So there's exactly 1024 numbers, binary numbers, characterizing what's going on inside this Atari. And those have to be enough to tell it what to do next. And inside the agent, we have some representation, which in our particular algorithm was just a stack of the last 4 things we've seen. And that was the information that we used to decide what to do next. Okay. Right. So let's open up an RL agent and see what's inside. So far, just to clarify, we've talked only about the problem. We haven't even mentioned how to solve the problem. We've just talked about what it is to define this reinforcement learning problem. So what I'd like to do is talk about the main components of an RL agent. What are the main pieces that go inside it? And I'm going to use that to build a bit of a taxonomy of how we talk about reinforcement learning. So an RL agent may include one of these 3 things. These are the main objects for reinforcement learning. They're not the only ones, so I don't want you to think this is an exclusive list. But these are the main concepts that we're going to talk about, the main pieces you may have or not have inside your agent. The first one is what we call a policy. So this is how the agent picks its actions. It's its behavior function. It's the way that it goes from its state to a decision about what action to take. The second idea is what we call a value function. This is the thing which basically says, how good is it to be in a particular state? How good is it to take a particular action? How much reward do we expect to get if we take that action in this particular state? That's the idea of the value function, a really central idea to a lot of reinforcement learning, estimating how well we're doing in a particular situation. And the third quantity is what we call a model, which is how the agent thinks the environment works. So not the real environment, but the agent's kind of view of the environment. It's got its own model of how the environment may or may not work. Okay. Now these are not always required for an agent, but these are 3 pieces that may or may not be used. Okay, so let's just go through them one by one. So the policy is essentially a map from state to action. So if we're in some state S, then we could have a deterministic policy. That's one choice. It's like just a function now. This function pi tells us how to get from some state S, summarizing the situation we're in, to some action A. This is the decision the agent takes. And so this policy is really the thing which we care about. We want this thing to, we want to learn this thing from experience, and we want this policy to be such that we get the most possible reward. So that's the game we're playing, is to try and, the brain we're trying to build is the thing that figures out this policy. We can also learn a stochastic policy. So there's no reason our policies have to be deterministic functions. They can also be stochastic, and often this is very useful. It helps us to make random exploratory decisions, for example, to see more of the state space. And so this is just a probability of taking a particular action conditioned on being in some state. So it's a stochastic map now from states to actions. And we'll talk about both of those in this course. Okay. The next central quantity is the value function. So let's really try and unpack this a little bit. So the value function is a prediction of expected future reward. So why do we need this? Well, we need this to say, if you want to choose between state 1 and state 2, or between action 1 and action 2, how do you choose between them? Well, we want to be able to choose on the correct basis, and the basis that we're trying to use here is how much total reward we expect to get in the future. So the expected future total reward is what we mean by a value function. So formally, we typically write it something like this. So this would be a value function. And the value function depends on the way in which you're behaving. So we have to index it by pi here. So if I was to have a robot which is falling over a lot, that robot will get a very different total reward to an agent which is standing up and or walking effectively. So the amount of reward that we get depends on the policy. And so the value function for a policy tells us how much total reward we expect to get going into the future. So we're going to look at the expectation over the future of the reward at time t, plus the reward at the next time step, plus the reward at the next time step. And we can also have this discounting going into the future. This is something that says we care more about immediate rewards than later rewards. So we'll understand this in more detail next lecture, but just to give you some intuition, this is a really central idea that we care about basically how much total reward we can get from some state onwards if we're going to follow this particular behavior. If I'm in my helicopter and I know that I'm going to execute some particular trajectory, how much reward will that trajectory get me? That's what we're trying to say here. And if we can compare these things, then we've got the basis to make good decisions, because we know which of those, should we choose the trajectory that's going to get us 73 points of reward in total, or should I choose the trajectory that's going to get me 65 points?